Okay, ladies and gentlemen, good morning. Thank you for coming to Professor Tajana Simunic's presentation on improving the energy efficiency of data centers. Professor Simunic is currently an associate professor in computer science in University of California, San Diego, and she's also the director of Systems Energy Efficiency Lab and leader of the Multi-Skill Systems Center Trust on energy efficient transport systems. Her research interests are energy efficient computing, embedded systems, and wireless systems. Tajana's work on event-driven dynamic power management laid the mathematical foundation for the engineering problem and devised a globally optimal solution, and more importantly defined the framework for future researchers to approach these kinds of problems in embedded system design. Our current work is focused on developing energy efficient scheduling policies for virtualized server environments and also energy efficiency in population area healthcare networks. From 1998 to 2005, she was a full-time research scientist at HP Labs, while also leading research efforts at Stanford. She finished her PhD in electrical engineering in 2001 at Stanford, and concurrently finishing her master's in engineering management. Her PhD topic was dynamic power management, dynamic management of power production, dynamic power management, same thing. Prior to pursuing her PhD, she worked as a system design engineer at Ortega, and she obtained her MS in EE from University of Arizona. She has served at a number of technical paper committees and is currently an associate editor for IT transactions and mobile computing. In the past, she has also been an associate editor for IT transactions and services systems. So welcome.
Thank you. It's a pleasure to be here. And we look forward to hopefully talking with you a little bit about how we improve energy efficiencies of large-scale data centers. What I'll cover in this talk will actually focus not just on individual data centers, but we'll also look at what happens if these data centers are distributed globally and connected by high-speed optical links. And what I mean by high speed is generally above 40 gig, because under 40 gig, you really don't have enough bandwidth to move the data around as efficiently. So some of the issues that come up when we have these distributed renewable power data centers is, first of all, energy becomes a big variable. As you all know, the cost of energy changes depending on where you live. If you happen to live in California, it gets really, really expensive. If you live in the Midwest, hopefully it's a little less expensive. If you live in certain parts of the world, it can be fairly cheap, in fact. The other big issue is if we start using renewable power, then the variability of this renewable power is a big problem when it comes to powering any kind of a system. In San Diego, we're lucky that we have a lot of sunshine, so solar power is great. The only problem with solar is you don't get much of it at night, so you kind of have to have a backup plan for the times when it's either foggy or it's nighttime. Wind power is also wonderful. In fact, we have a lot of wind farms in California. The problem with wind is that it's much less predictable as compared to solar. So in both cases, we need to actually have some techniques that estimate the potential for energy availability and that can then leverage this information when making decisions on what type of energy to use and how to use it. The other big issue is that data center energy needs are generally much higher than what you would actually get out of any kind of local green energy supply. So typically you would use green energy as a supplement, not as a mainstay, unless you happen to run a really small data center, such as the container that we have at UCSD. So generally, all of the work that we have focused on assumes that green energy is going to be a supplement, and there'll be some level of brown energy that is leveraged. The other issue is to make this green energy availability a little bit more useful, you have to develop data centers that are very energy efficient to begin with. So there's quite a bit of work that we did that looked at how do we both leverage power management techniques and develop new power management techniques within a data center, and how do we reduce the cost of overhead that's involved with data centers. Specifically, we looked at overhead in terms of power distribution network and in terms of cooling and thermal management. So I'll touch on some of those ideas as well. The next issue is that data centers generally are there because we want something from them to do. So we want to have workload that we send done in a very timely fashion. And in fact, a lot of the large-scale data centers run jobs that require very fast turnaround times. So typical response times for web search are on the order of about 100 milliseconds, and this is measured from the moment that a request actually enters the data center. It also considers all of the different parts of the data center that happen to be involved in coming up with a response to the request that came in. 100 milliseconds may sound like a lot to those of you that are used to using relatively simpler systems, but it turns out it's actually a fairly difficult deadline to make if you have a whole bunch of servers involved in the system. In addition to this, in order to make this 100 milliseconds possible, you normally have to run a whole bunch of background jobs that analyze the data and get the data ready to be very easily reachable when the particular service request arrives. So in a typical data center, you will have roughly two classes of jobs. A class that I call service jobs, which tend to be much more latency sensitive, and a class that we term batch jobs, which are really more throughput based. Still, there's some sensitivity in terms of performance, but it's not on the order of milliseconds, it's on the order of seconds to minutes to even hours, depending on the type of the job. So we need to be able to actually somehow run all of these jobs concurrently. In today's data center, typically the jobs are run on separate machines. So you'll have a machine that's dedicated to web search, you'll have a machine that's dedicated to email, you'll have a set of machines that are dedicated to just processing data. The reason for this is actually kind of interesting. It doesn't have to do with the fact that the servers are overwhelmed with the amount of processing that web search or that email brings to them. In fact, it's quite the opposite. Typical utilizations for those servers are around 20 to 30% at the CPU level. The problem is that today's systems don't have a good way of guaranteeing performance if you run more than one type of a job on there. So this is one of the questions that we have targeted in our research, and as I'll show you later, we developed a virtual machine-based system that can, in fact, guarantee performance guarantees for services and will also be able to meet a certain level of throughput for the batch jobs after those jobs are clustered together. And this is one of the ways that we've been able to improve energy efficiency. And then lastly, to make all this possible, whenever you talk about clustering things, it involves movement of data. So fast networking becomes really an important thing to have, both within a data center and also outside of the data center. And within a data center, when you go beyond top of the rack switches, the networks are severely oversubscribed today, so you're starting to see in large-scale data centers quite a bit of congestion. And this has actually resulted in a push for including optical networking at the layer of the cluster. Outside of the data centers, if you do any experiments that involve migration of larger jobs across 10 gig link, you discover very quickly that 10 gig links are too slow, and that moving large chunks of data simply takes too long. So to do any kind of live migration, you need to go faster at about 40 to 100 gig. And the other issue with wide area networks is that their energy efficiency has actually not been even thought of. Mostly, wide area networks were designed to deliver a certain level of bandwidth. So typical SLAs involve negotiation around what level of bandwidth will be delivered to a particular company that is leasing the network. The companies that actually run these networks, in their case, if you look at their profit margin, a lot of the profit margin will in fact go to cost of operating the network itself. What goes into operating the network involves powering the optical links, which is fairly flat level of cost. The moment you turn the laser on, the link is basically turned on and consumes more or less fixed power. The variable part in this story is the routers that are present throughout the network. And routers, as you'll see towards the end of my talk, are not designed to be energy proportional at all. Even though they can be, there's nothing ultimately stopping you from delivering energy proportionality. So I'll show you also some results that analyze how we can reduce the energy cost of wide area networking as a result. So to start out, I would like to first address the question of how does one increase data center energy efficiency inside of the data centers? And then I'll talk about what do we do if we have a whole bunch of data centers that are distributed globally. So inside of a data center, you typically have a bunch of servers, but then you also have a whole bunch of supporting infrastructure. The supporting infrastructure involves things like UPS batteries, which are there in case electricity dies. UPS batteries typically buy you about 5 minutes worth of time of running the servers. The 5 minutes is enough to actually get diesel generators up and running and ready to produce electricity on a more permanent basis So batteries, in this case, are not designed to, in fact, run data center for a very long time. The rest of the time, during normal operation, this UPS system does absolutely nothing. So it's essentially overhead onto the system. The next big thing that probably all of you are aware of, servers tend to like cooler temperatures. In the past, this was around 20 degrees. Today, the temperature has crept up closer to 30 degrees, depending on who you talk to. Either way, you actually do need to have a supporting subsystem that at least blows the cool air in the correct locations. And in a lot of state-of-the-art facilities, people still use hot aisle, cold aisle containment, and HVAC to ensure temperature distribution is relatively flat and cool. This is because you want your servers to be as reliable as possible. Typical window for replacing servers is every 3 years. So within those 3 years, you really do not want to see failures, if at all possible. And this is basically what's behind all the cooling infrastructure. Cooling infrastructure, as you know, is also overhead. And this is generally formalized, if you look at the data center energy efficiency, as a power usage efficiency factor. So in the past, power usage efficiency factors were around about 2. In state-of-the-art facilities, they're around 1.1. The thing you should be aware of when they talk about power usage efficiency being close to 1, what they're talking about is anything that's outside of the server, that does not address any inefficiencies that happen inside of the server box. And there are quite a few inefficiencies that happen there as well. And the other thing I wanted to mention is this distribution, which is fairly well known. This comes from Google, that shows you the distribution of CPU utilization. So you can see on the x-axis CPU utilization, on the y-axis the probability essentially that you spend that much, that you spend time at that level of utilization. And by looking at this, you can see that most of the utilization of servers is around 30%, which again has to do with this need to deliver on response time requirements to the users. So if you talk to people at Google, they'll tell you that going much outside of that window, they've shown will cause a fairly large profit loss, which will in return provide a huge motivation that this never happens again, obviously. So they're willing to waste a lot of energy in order to be sure that performance needs are met. On the other hand, the bad news is that servers really are not proportional with energy at all. So if you look at the same axis at about 30–35%, you're near about 90% of the peak power usage in a server. So what this basically tells you is in order to meet performance guarantees, you're wasting almost 70% of energy effectively. For really no good reason, other than the fact that there is no way to currently meter that performance and provide feedback into the control system that enables you to allocate jobs appropriately, and there is no good way to actually scale the server energy cost. So to kind of review and recap, what is efficiency? When we talk about efficiency, what I really mean is the amount of computation you did for the total amount of energy that you put into the data center to get it done. And in the work that we did in my group, we focused on both aspects of this. We looked at how we can increase the amount of computation for the same amount of wattage that goes in, and also how we can decrease the total energy cost within a data center. This efficiency can further be represented as the factor between power usage efficiency. This is a metric for the data center infrastructure, so everything but the server. Then server power usage efficiency, so this would be inefficiencies within the server. So for example, all of the cooling subsystem within the server is loss in terms of efficiency. Also, all of the power conversion subsystem within the server is also lost because you have a lot of DC-DC and AC-DC converters within the system. And then lastly, the good news is the computation to actual energy that goes to components that do something useful. So your processor, your memory, and so on. So to give you a quick overview of some of the strategies that we developed within a data center, a lot of this work has been motivated and has been done by using the data center container that I'm showing you here on the picture. This container was funded by NSF Greenlight project. It enabled us to run 8 racks worth of systems and to have the systems fully instrumented. So we can actually measure just about anything you would imagine within this system. And as a result, we're then able to develop fairly effective techniques for both dynamic power management and also for dynamic thermal and cooling management within the data center. So in case of dynamic power management, we developed in recent time, in fact, paper is going to come out this year, on adaptive power gating, which allows us to save about 40% of energy with no performance overhead at all. What basically happens, this is at a very low hardware level, we're able to turn off a whole processor without losing any of the context and turn it back on in time frames that range from 6 to about 16 milliseconds in a multi-core processor that's similar to a Xen from Intel. This work, if you're interested, I'll be happy to talk to you more about later. I will not actually cover it in this talk. The next thing that we worked on, this was work done with Intel. As I mentioned earlier, these response times are a really big deal for any kind of service job. So one of the questions that we asked is there a way for us to provide a target level of response time with fair certainty and at the same time reduce power cost as much as we can? And it turns out that using some relatively simple control techniques and very new performance counters in Westmere servers, we're able to show that we had about 92% reduction in performance variations with about 17% reduction in power. So in this case, the target goal was to really meet that performance limit as much as we could. The topics that I will actually cover in this talk are on how we developed virtual machine energy management system that allows us to co-schedule multiple different types of virtual machines on a single server and without necessarily violating the quality of service requirements. And this resulted in energy efficiency gains of up to about 70%. And then towards the end, I'll talk about how we were able to reduce the cost of peak power by using distributed batteries. And so some of you may know that Google, instead of using centralized UPS in order to switch off from utility power to the diesel power when utility goes down, they actually put batteries with servers instead. So the question that we asked is, can we use these batteries during normal runtime? And it turns out if you're careful which batteries you have and how you design the system, you can actually shave a fair amount of peak power at no performance cost whatsoever. So this work will appear in this year's ISCA. And I'll, as I said, talk about it a little later. Now, one of the themes that you can see here is that generally a lot of the focus of the work has been to see how we can increase the amount of computation while decreasing the number of servers that are running that computation, because that ultimately will help me in improving energy efficiency. The problem with this idea of clustering as many jobs as I can is that that actually increases the average power of the server itself, and as a result also increases temperature. And as I mentioned earlier, temperature is an issue not because I particularly care how hot it is, it's an issue because of reliability. A lot of the failure mechanisms are an exponential function of temperature. So this is why you have a sophisticated cooling system in data centers. And this is why we started considering not just power, but also thermal and cooling management. So we developed proactive thermal management techniques which monitor temperature in various parts of the system, and based on the monitored data, will predict what is likely to happen in the near future, and then using this prediction, we'll proactively schedule workload to avoid creating hotspot areas. And then more recently, we have developed cooling-aware management techniques that enable us to schedule workload jointly with fan control. So this way we can utilize cooling subsystem much more effectively at much lower cost. So to get started, I just wanted to give you a sample of what the data from our Greenlight infrastructure looks like. What you see on the left here is the container level data. It shows you temperature, humidity, and current power usage efficiency and current power levels within the data center box. In the middle, what you see is the racks. So there are 8 racks, so therefore 8 columns. In each column, you can see the fan speeds and also temperature distribution per rack. And if you click on any individual area, you can see the power consumption. And then if you zoom in further, you can see power plots for every individual server. We can also get detailed power data within the servers. That actually has been done for only a few sample machines because, as you know, there are no power sensors inside of these servers today. Some of the newer machines actually are coming out with power counters, which are very similar to performance counters, that have been calibrated to give you fairly accurate data on power consumption of the processor within the server.
This is a chip level?
This is a chip level right now. So the Sandy Bridge has it. But I would imagine that similar idea is going to be applied to memory and to the rest of the subsystem because it's relatively simple to do. So I think the concept of monitoring performance and power in real time and then making decisions based on that makes a lot of sense in reality. Yeah.
But if you can use temperature sensors to in some sense decode the power plant as well.
You can, it's not as accurate because it's a strong function of what happens around the system. Temperature, as you know, is really more of a low-pass filter. So if I happen to have a bunch of hot servers around, if I happen to have some strange fan configurations, so for example, in this container, the fans are at the rack level as well, that will strongly influence what kind of temperature you see. So you either need to be aware of what configuration you're in order to adapt your power estimate, or you need to use some additional information. So, and I really honestly don't see a problem in adding these power sensors in hardware. People just didn't need them before, so they didn't add them. And there's nothing difficult about calibrating a power performance camera post-production. Yeah.
Out of curiosity, right now, what is the percentage of the power that's consumed by the processors?
Depends on the server. So servers that tend to have less memory will have higher percent of power due to the processor, so about 40% maybe. Servers that have a lot of memory, so for example, if you look at Oracle database type server, the fraction of processor will go down. But then the fraction of power due to memory goes up, and due to fan also goes up. So the more memory you have, the more fan speed you're going to have. Which seems counterintuitive, but if you consider the fact that memory is always on, then you realize that it actually makes sense. And memory's critical temperature is in fact lower than the processor. And then I'll talk a little bit more about actual layout and this whole cooling problem.
So it brings us to the question: it's 30 degrees Celsius constraint that we have at server level. How is that?
The 30 degrees is outside. It's not inside of the server. So it's an ambient temperature. If I stand inside of the box and it measures temperature where I'm standing, that's the 30 degrees.
But why? Why 30?
Because when you go inside the server from that 30 degrees, you get an offset of almost 20 degrees. And if you put 50 degrees ambient right outside of your processor, and you look at critical temperatures on the die, they actually go up to 125 very quickly.
But then if you have,
so that's the trade-off, basically.
Fine, but if you have calculation with the sensing going on at chip level, which this is what something that you have,
yes,
and power sensing and temperature sensing, one
yes,
could see that you could set up a control problem which is controlling the temperatures and power at chip level and not caring that control.
Certainly, except if the chip gets too hot, there isn't much you can do other than hit performance. And hitting performance is a bad thing in general. So if you talk to Google and tell them, I'll make sure that your temperature never goes above 125, the first question they're going to ask you is, and at what performance cost? And if the answer is more than 1%, there's nothing to talk about.
Yeah, but that still doesn't justify a need for an air temperature constraint, right? I mean,
it does because it defines how far you can go with performance. So performance and power are intrinsically related. Power and temperature on the die are also directly related. So if I increase the ambient temperature by 20 degrees, I'm basically increasing the on-chip temperature by also about
but that would be my feedback control to fix. But saying that I'm
Except the only way to fix it is to actually slow down. So if I'm running at high levels of utilization, which is what I'm aiming for in these systems, my goal is to use the servers as much as I can and deliver performance, right?
But fine. The question is, does one need to say that one need to fix the temperature problem is to have the air temperature efficiency sensor? They're saying that all servers at all times need to have an ambient temperature of 30 degrees is a very severe constraint. And if you have a control mechanism which is controlling the chip level, sometimes even if the temperature of the air is 40 degrees Celsius, it's probably okay.
I think there are a number of issues here that are involved. It's not as simple as, I'll just let the temperature go up to 40, because you have to remember within a container, it's not just one server. There are 8 racks within a container, and each rack has maybe 20 servers.
Sure, but
so,
if I can,
and it's one ambient temperature.
Fine, but if
I
can measure the temperature of all the 20 servers with all...
So as I said, the problem gets a little more complicated. That needs the eye, and I would suggest we do this offline,
sure.
Given the time. So using this measurements...
So quick comment. So for this ambient temperature, I heard from people probably from Microsoft. So they're talking about, if you measure about raising the ambient temperature by 20 degrees, that can be a huge problem. But they said that if you change it by 2 degrees, it doesn't matter that much.
Yeah.
But if you're considering the the electricity bill. If you can raise the temperature by 2 degrees, you save a lot of money by
Yes,
raising
and
that.
that's what people are doing.
And then they used to be set at 25, they changed it to 27. So I think, I mean, when you assume it's 30, it makes perfect sense to me.
Yeah.
And another question there is, you measure this chip level temperature, right?
We measure chip level, socket level, memory level, board level,
Okay.
next to the power supply, next to the hard disk.
So in
And actually
general,
on chip, there are about 30 sensors that measure
About 30
temperature, and memory, depending on memory who you got it from, there is at least one, and oftentimes more than one.
so it's per chip like 30 temperature sensors.
Yeah, there are a lot of
Okay.
sensors.
Okay.
Not all of them are necessarily visible to all operating
Right.
systems, but there is a lot of data to be had. Yeah. Yes?
Like in a different subject, like you mentioned about the peak shaving using the batteries. How much the price plays a role in this system? How much do you, I mean, how much do you care about the cost?
I do, and I'll get to that. So for power question, as you saw a second ago, I can measure temperature, I can measure fan speeds, I can also measure power consumption. One of the obvious questions that always comes up is, if I decide to move jobs around, what will that mean in terms of the new power consumption at the new location? And in order for me to decide what it means is I need to be able to figure out how much power the job is currently consuming at the particular server where I'm running it, and then estimate how much would it consume if I moved it somewhere else. This is a classical problem when we do any kind of migration. So the goal that we set out was to estimate how much a particular virtual machine consumes, assuming that there's more than one virtual machine running on a server. So this is not a simple world where you have just one job. And we ran a bunch of experiments. So here is an example of what we saw. At various CPU utilizations, depending on what type of jobs you run, there's actually a fairly wide spread of power numbers that you get. In fact, what we saw on a particular processor was about 70 watts at exactly the same utilization level. So in order for us to be able to detect something like this, you can't use just a CPU utilization-based power model, which is what people traditionally have used. And in fact, it turns out that you can't just use CPU utilization and performance counter model, because you still don't get nearly as good accuracy. So what we did is we used Gaussian mixture vector quantization, basically in order to detect some of these clusters of data that come from different types of jobs. And we were able to show that we can get about 3 times better performance in terms of prediction error than doing either linear regression, so linear regression used CPU utilization only, or compared to multivariate regression, where we used exactly the same variables as inputs as our Gaussian mixture model used. And at the end, we end up with an error in prediction that's under 10% on average at various utilization levels. So at under 10% prediction error, generally I would assume is more than good enough, because your measurement error is not all that much better anyway.
So on the CPU utilization figure, so can you read the legends of those 5 different things? The left, the one on your right.
Oh, these are different jobs, different batch jobs. These particular jobs came out of, I think, spec benchmarks.
So spec
This is a processor power, right?
This is processor power as an example. Memory power is more or less a flat line, because there is no power management that's happening in today's servers. And that kind of basically means that most of the server, other than the processor, is going to be fairly flat.
So basically those are 5 different spec benchmarks, not 5 type of different tasks.
These are 5 different benchmarks running at different utilization levels. It's just an example. All we wanted to do here is show you that if you use utilization, you're not going to get a correct answer for the power. That's really all that's meant by this. Okay, so the next step was to basically ask a question of what happens if you actually consider more complex workloads. Spec is nice if you do architecture research, but if you're looking at energy management in data centers, you need to consider jobs that are multi-tier jobs that have dependencies. And you need to consider then service response times as another metric of performance. So in this particular example, we used Rubix, which is an auction website similar to eBay. And Rubix basically have clients that send requests to the web server, that sends requests then in the backend to a database and fetches the responses back to the client that requested it. If we actually run Rubix in one VM, on a particular server, you'll see that service response times are generally very easy to be met. They're well under 100 milliseconds if I assume that the database server is in relative close proximity. to my web server application. If, on the other hand, I add another virtual machine onto that same server that runs some batch job, what happens is our SLA ratio, so this would be a ratio between the target response time on average versus the actual measured response time. So numbers that are under 1 are good numbers on this y-axis. As soon as we add a batch job, we actually reach a ratio that's close to almost 20. So you can really destroy your performance extremely quickly. This is obviously a function of what type of a job you happen to add. You know, in some cases, you won't see much interference. In other cases, you can see really huge interference. So clearly, the unmodified Xen was not able to actually keep track of this. From Xen's perspective, there were more than enough resources, and you can see that CPU utilization is in fact about 50%. There was more than enough memory. The problem was that these jobs happened to be contending at the cache level, and you have to monitor in this case. You can also have contention at the network level. So there are multiple different layers where this can happen. So what we did is we modified Xen with the ability to monitor response times and to monitor where the contention actually happens, and then adjust the allocation as appropriate. And running exactly the same example, we're able to get more than 10x improvement in SLA. So now SLA is under 0.3, which is well under 1. And we still run 2 jobs instead of just 1 job on exactly the same server. Our CPU utilization is, again, a little higher than it was before we added the batch job. It's about twice as much, almost. It's still not 100%. So from this figure, it still seems like we have some headroom to add additional jobs if we want.
So good question. What's the motivation of mixing these two? Usually they don't mix latency sensitive and frequency jobs.
They normally don't mix them. They normally don't mix jobs because of the problem with latency-sensitive jobs. They want to ensure that latency actually is met, and they don't have a very good way of ensuring that. So really, that's what was missing in the whole story. So what we did is we decided to monitor batch jobs, which are throughput-driven, monitor latency-sensitive jobs, so services, and use these various metrics to then make decisions on which VMs will play well together. These decisions are monitored by using what we call QoS ratio. We define the ratio because even within a single service job, we may have different types of response time requirements. So for example, if I'm using Facebook and I'm uploading video, I'm much more tolerant to the delay of that than I am to just posting a comment or doing real-time chat. So QoS ratio enables us to actually quantify these differences much more easily. And our goal now was to maximize energy efficiency as a function of Q, which is the quality of service ratio, and then bandwidth per watt, which is basically how many batch jobs can I run as effectively as possible per watt that I'm spending on that particular server. So the way we did this is we used actually initially just a virtual CPU allocation metric. We had since worked on also memory and are currently working on the network aspects. We use state space control because we wanted to be able to guarantee stability. So you don't want to be flip-flopping these batch jobs a whole lot. You really want to converge to reasonable value. And you can see from this picture, and this is somewhat shrunk version of the simulation, that if we use our virtual CPU allocation method, as the QoS ratio skyrockets, we're able to very quickly adapt and achieve a reasonable allocation for both of the types of jobs. And to show you a better comparison, we ran a baseline example. In baseline example, we ran services on one set of servers, batch jobs on the other set of servers. So this is what a typical data center would have today. Secondly, we used selective consolidation, where we just monitor performance counters and had no concept of quality of service. Third, we used CPU capping. So this is work that was published in 2009 and 2010, where basically allotment of batch virtual machines of the CPU was artificially capped to ensure that services get enough CPU time. And then we compared this to our controller. And you can see from this picture that our controller is 70% more energy efficient than the baseline. And this is primarily because you now need less servers. So we have clustered the jobs. But what's more interesting is that we're 35% better than the ideal version of state of the art. And what I mean by ideal is these two types of algorithms have no way to ensure quality of service. So what we did is we ran these algorithms as far as we could to the point where they met quality of service, and we report comparison to those results. In reality, if you actually use these algorithms, they will violate quality of service because they can't measure it. And we did all this while still ensuring that the throughput for batch jobs was within 7% of baseline. So the performance hit to batch jobs was about 7%. Which, if you consider the fact that we now have half as many servers effectively, is actually a really good deal. And so the results of this work have since been implemented in some of the Oracle systems. And my student is now working at Google in their cluster management group and working on implementing some of this there as well. So what you saw thus far is the fact that we tried to cluster as much stuff as we could, and we run it as fast as we can to ensure that performance guarantees are met. This basically means that you've got a problem with temperature generally. So if we start reaching utilization ratios around 70, 80, 90%, generally you wouldn't want to go much higher than this. You start getting hot. So to understand this a little bit better, what we did is we took workloads that were collected in a data center. This was at Oracle's data center. And we used systems thermal properties. Again, this was monitored within the servers in our particular container. And it was also simulated because we cannot control the fans. So as a result, we couldn't completely control the temperature distribution. So the results that I'm reporting are results that are calibrated against measurements, but actually simulated. So the first thing that we did is we took the known server workload, we ran it using a Linux scheduler, and we monitored how temperature behaved. And as you can see, for a certain fraction of time, we end up with hotspots on the chip. The red area is the hotspot time. Secondly, we took exactly the same workload, and we came up with an energy optimal way to assign it. So we looked for minimum energy cost with no thermal performance constraint. And what you see happened is we still have about the same amount of hotspots. The reason for this is that the workload got clustered into as few areas of the die as possible, and the rest of the system got shut off. So effectively, if you happen to cluster it in the wrong area of the die, it just got really hot. And then lastly, we did thermally aware optimization, where for obvious reasons, because temperature is a constraint, now you don't have a thermal problem. The trade-off here is that you have less energy savings because there was less clustering that was possible. Performance-wise, these two policies don't behave all that differently. Both of them have some performance hit relative to just load balancing, but no thermal.
But you would believe that load balancing will have a similar impact as thermal optimization, because effectively what load balancing will do is sort of distribute the workload all across the die.
Yeah, that's a common misconception. So load balancing does distribute it for performance reasons, so it's going to look at queues essentially. What it doesn't look at is where those queues are. So if I happen to have 8 processors on the die, and they're numbered 0 through 7, and 0, 1, 2, and 3 happen to be next to each other, and your scheduler decides to count from 0 when it starts assigning, what's going to happen is 0, 1, 2, and 3 are going to be hot. And in fact, your core number 0 is going to fail a lot sooner than your core number 7. And this is actually common to both on-chip schedulers and it's common to grid schedulers as well. So when we talk to Supercomputing Center, they use the very well-known grid scheduler that probably a lot of supercomputing centers use. They actually assign workload alphabetically. So if your servers start with letter A, they have higher chance of getting workload. If they start with letter Z, they have lower chance. So predictably, A's are hotter than Z's. They didn't need to. Temperature was not an issue. So basically, the assignment had to do with performance only. It didn't have to do with power or temperature. So there's really no reason why you wouldn't. And in fact, I'll show you in a second that simple randomization technique helps a lot. And you can do even better if you use some informed scheduling, obviously.
But at a server level, you would believe that the distance that you have between processors, between servers, would be accounted for in the performance to load balancing.
Not necessarily, because when you load balance, you oftentimes want to keep cache affinity. So if cores happen to be sharing L2 cache, yes, you're going to tend to assign them next to each other, which again creates heat dissipation. So load balancing really targets performance. It does not target either power or temperature. So most of the traditional thermal management techniques are very reactive. What they do is they wait for temperature to get hot, and then once it gets hot, they will respond by either scaling down voltage, by fetch gating, by migrating workload. If things are really severe, you will completely shut off a particular processor. Instead, what you want to do is you want to be proactive. So you want to be able to predict what temperature is going to do, and based on this prediction, assign workload in a way that doesn't cost you performance, but that hopefully spreads out the temperature distribution. So this is the work that we did a few years ago. We did it by using thermal data from the sensors on the die. We developed an ARMA-based predictor. We also developed a few other predictors since then that are lower overhead than ARMA. And then based on the prediction, we will then schedule in thermally aware manner. Now you'll notice that we have to do periodic ARMA validation and model update depending on how much workload has changed and how much, therefore, temperature characteristics might be changing. So here's an example of what a real corner case might look like. If I run workload and then shut off the core and run it and shut off the core, you'll get this kind of temperature profile. This is actually x-axis in seconds. That's why it looks more severe than it in fact is. Typical thermal time constants on the chip are about 10 milliseconds and above. So what you see here is that our measured data and our predicted data match really well, and when there is a change, we detect it very quickly and we're able to adapt to it very quickly. We do this by continually monitoring the data and comparing to what our predicted values are, and then we use the measurement of the error as a part of our sequential probability ratio test to determine whether we should in fact be updating the ARMA model or not. The reason why we use SPRT is because it guarantees the earliest detection. So ARMA model is shown right up here. T here is the temperature sampled at particular time t. A and C are coefficients, and the error is the error between measured and predicted value. For adaptation, we'll first go through a step of identifying which ARMA model we should use. This would be the P and Q parameters you see on these suns. You start from the lowest model and go up. In practice, it doesn't take actually a very high level model for most of this temperature. It is higher level than just simple exponential because exponential doesn't catch these corner cases of a lot of on and off. Then we, after coefficient estimation, we check the model again to ensure that we got within reasonable tolerance of the. So when we implement this in a real system and compare it to default load balancing, our proactive thermal balancing actually will decrease incidence of hotspots by about 80%. It does this with relatively small performance hit. The performance hit happens only when you're in very highly utilized scenarios, in which case you either have to slow down or you have to shut off, so you can't do much about it. The results for default load balancing disabled any kind of thermal management. So effectively what we have happened here is you either have gigantic fans that would absolutely guarantee, or your chip burned up. So they're fairly idealistic. So going forward, as I mentioned, fans are there. You want to use these fans effectively. The problem is that fans today operate only as a function of the thermal sensors. They're completely oblivious to any kind of workload scheduling and management. And fan power, in fact, is cubically proportional to fan speed. So for every notch up in fan power, you're paying a lot more in terms of energy. This is especially the problem if you have systems that are very memory dense, where fans are fairly big, and every notch is actually a huge amount of power. So in a typical system, you'll have fans that are associated with each socket, and then that warmed up air from the socket will blow over the memory DIMMs, attempting to cool the memory. This, as you might imagine, is not an ideal situation for memory because the critical temperature there is actually lower than the CPU temperature, and because it gets hotter ambient air than the CPU's get. So what we did is we formulated a state space control to ensure that we can get stability between workload scheduling, thermal management, and controlling the fans. The controller will decide what kind of CPU power distribution we need, what kind of memory power distribution, and what to do with fans on every tick, and then the actuators will actually implement that. I'm going to skip through this. It talks about the controller. There's some fancy math. Basically, it converges fairly quickly, and it's provably stable. When we combine this and implemented this for Intel Xeon dual socket server, you can see a picture of our setup where we measured everything. You can see that our cooling savings are about 70% relative to state-of-the-art. This is a savings just in the cooling subsystem, so this is not the overall server power. And those cooling savings come at very small performance overhead. It's under 0.2%. right now. So for very small price, you actually get a fairly good result.
Do you have data as to how much the values were for the fan power?
Don't remember for this exactly. I do know that it was about 30% of the overall server power.
30%.
Yeah, so it was about 30 watts. I don't remember the exact value. So thus far, I told you a whole lot about what we did with servers. How we clustered the workload, how we reduced the temperature, and so on. What I would like to discuss now is what do we do for the rest? So how do we deal with power infrastructure and utility bill, which is fairly high? So somebody asked in the back this question about power. So typical large-scale data centers will make agreements with utilities to deliver a certain amount of energy over a period of, say, a month. At that level of power is what you could call a peak power line under which power is cheap. Anything above that peak gets actually charged at much higher rates. These rates can be about 5x of the negotiated amount. So there's huge amount of incentive to keep power under the peak power, obviously. And in fact, in case of Duke's energy tariff utilities, the power above the peak was at $12 per kilowatt. The power under the peak was at 5 cents, so gigantic difference. So at the end of the month, even for relatively short, in terms of time duration, moves out of this peak level of power into the expensive power, you can in fact have 50% of your monthly electricity bill go just to that. So typically people, when they talk about peak reduction, they have used strategies such as voltage scaling, consolidation, and shutting off servers and so on to try to reduce the cost. But all of these strategies result in fairly large performance degradation. If you shut off a server, you don't have anything to run. If you scale voltage, performance hit, as you know, can be pretty dramatic. So recently, there was actually work proposed at this guy in 2011 to use the UPS, centralized UPS batteries as a way to shave part of this peak power. And what they got is about 8 to 16% savings in utility bill with about 4x over provisioning. So a fairly large amount of over provisioning for relatively small benefit.
Sorry, what do you mean by over-provisioning?
Meaning that you have to get 4 times bigger UPS subsystem in order to actually be able to shave any reasonable peak power to get the 8 to 16% result.
So 4 times what you need is just to keep the system going for 5 minutes.
Longer than 5 minutes, because now you're shaving peaks of power consumption that are longer. You're not just trying to tie you over until diesel starts.
But that's the baseline you're competitive against.
Yes.
And how often does this happen?
Peaks tend to happen in the middle of the day, so usually at the worst possible times, because electricity is expensive.
Does it happen every day?
And not every day. I will have to look at the data, but we found corner cases about 20% of the time, maybe. So if I look at 20% of the days in the year, there would be a spike in workload that goes beyond normal.
So you push one direction and it pushes back, so you need more bandwidth.
So that's why it was 4x over provisioned.
But so how much more does that cost you in relation to the 5 cents to $12 that you mentioned before?
So I'll get to that. Yes.
Excuse me, while you are comparing above the baseline in terms of power, below the baseline in terms of energy, it's not a fair comparison.
Yes, the cost, that's why I said that the cost is effectively about 5x.
I know, but I'm saying why one, if you go back to 2 slides.
So, no, I understand what you're saying, but energy is billed at monthly periods, so I know exactly how much time it is, which means that I know what level of power, and this is negotiated level of power. So there is a line essentially that you negotiate. This is why all of these plots have a line through it. If I go above that particular level of power, data center level, I get charged peak tariff.
I understand that. I'm saying why above the baseline you're talking about power, below about energy.
Because
why
that's
also not
the
energy?
contract. Contract is written exactly in those terms. So when you make a contract with utility, it's for energy, it's not for power.
Exactly.
When you get charged for peak power, it's 15-minute windows, and it's amount of power above the baseline that you negotiate. It's basically how this is done in business.
So when do these
It's not because I particularly want to do it.
When do these barriers kick in and when do they stop?
So I'll talk about it in a second. So what we worked on is using instead distributed battery systems. So I mentioned that Google actually distributes these batteries, and we went a step further and evaluated alternate battery technologies and how those could benefit as well. So we did total cost of ownership analysis, and I think this is what you were asking about. Details of this work are going to come out in ISCA this year, so I will be happy to share the paper with you. The key benefit is that we saw about 1.5x profit increase per server with respect to the original centralized policy. And we're able to shape much wider peaks, and I'll show you on the very next slide. So the technologies we compared are the lead-acid battery, and this is the original centralized policy that ISCA in 2011 presented. And we also compared this to lithium iron phosphate batteries, which are much more energy dense and have a lot more charge-discharge cycles. So lead acids are actually fairly limited. You can do at most one charge per day if you want the battery to last any reasonable amount of time. What you see on this particular plot is on the x-axis is the duration of the peak pulse. On the y-axis is the size constraint for the particular battery. So this one line that you see through here is the maximum size of lead acid battery that you could buy and put next to a server to still fit within the rack. Same thing is for the lithium iron phosphate. Those batteries are slightly smaller, so this is why the size is slightly bigger. And you can see that with lithium iron phosphate, we can actually shave fairly long power spikes. Because obviously this is much more energy dense. The negative side of lithium iron phosphate is that it's more expensive. You pay higher cost up front. The benefit you get is you can charge it and discharge it a lot more, and you get higher energy density. And it turns out for this particular application, it actually does make sense to pay higher upfront cost. The data that we took to analyze this came actually from some of the Google's workloads that were reported online, from the data that we got from Lawrence Berkeley Lab on the pricing and on the contracts that get negotiated. The battery management policies we compared are centralized, where we basically monitor if there is any available battery. If there is, we'll use it to discharge. If the battery is in use, then we obviously can't necessarily continue to use it indefinitely. We'll use it up until a certain threshold. This threshold is defined as a function of the battery characteristics. So you can go only to a certain level of throttle discharge before you come to a no-use node for the battery. And then our goal is to recharge during the times when electricity is relatively cheap. So if you use centralized UPS, you're going to recharge in general during the night, and this gives you only a chance to shave one peak power peak that's about 8 minutes long at most during the day. This is, again, I think it was reported in the work at ASPLOS last year. In the work that we did, we also used distributed batteries, so the controller changes a bit, because now we monitor data at both cluster and PDU level, and we're able to then be a little bit more efficient in terms of how batteries actually get discharged as a function of the particular load that we're experiencing in the game.
Sorry, kind of a question.
Yeah.
You mentioned that in fact when you measure the power consumption, that you measure it over 15-minute window, right? But you also
That's how you get built.
Right.
We measure it more often than that.
Right. So for the purpose of building it.
For the purpose of billing, you look at 15-minute window, the amount of time and the length of the peak.
But if your batteries can be drained for only 8 minutes, that shouldn't really buy you that much.
So that's the criticism of these work.
Right.
And this is why we propose to use both different type of battery and a distributed policy. Because we can shave, as you can see, peaks that go to multiple hours. Yeah. So that's exactly it.
In both cases, either distributed or centralized, you need to have 5 times more batteries?
No. In centralized, you have to have 4x more batteries. In distributed case, it's 1 battery per server. All of the size shown right here. So under this size constraint.
And how often do you need to change the battery? Replace the battery?
We actually calibrated it to 3 years because you change servers every 3 years. So to simulate this, we took a 1,000 machine cluster, which is basically our container.
Yeah. Back to your last comment, that you have this backup with the batteries. Does that change the tree going into the video?
No, so we have to account for that. in fact. So basically what we did is we allowed it to discharge, not to the full depth of discharge level, but to the level that gives us still the 5-minute window to tie us to the diesel generator. So we actually discharge less. It's basically a higher threshold.
But I mean, the related question is that batteries are also susceptible to temperature issues. So does that change?
It doesn't, because lithium iron phosphate actually is sensitive to fairly high temperatures in data center, as I mentioned, around 30 degrees Celsius outside of the rack. This doesn't cause any problem at all. And you can go, I think, up to 70 plus degrees. There's no way you would see that outside of the racks.
And what rates do you discharge the batteries?
At what rate?
Right.
These batteries are calibrated to discharge at the level of the current draw of the server itself. So 12-volt battery, you figure 300-watt server. That's the current. So we picked the size battery and the battery discharge current characteristic that was appropriate for that. So you can buy these actually in the market. There's nothing magical here.
I understand, but if you discharge a battery in 5C versus 1C,
that's what I'm saying. We picked the value of the discharge current that made sense for that particular size battery. So I start from 12 volts at 300 watts. That gives me the current, right? And then I look up batteries in the marketplace at what level of that discharge current will I get a nice characteristic.
So you choose a battery to get 1C.
Yeah.
You might oversize it significantly, and you might lose a lot.
Totally true. I'm not saying this is perfect. I am saying it is still over-provisioned, but it's over-provisioned on purpose, partly, because I can't completely control exactly how this is going to discharge and how it's going to behave over time. My goal is to make it to 3 years. Right?
I mean, come to think of it, buildings are probably designed at twice the level of strength that they need to.
Yeah.
Over-provisioning is something
No,
that is pretty standard.
It's true, and I think there are ways to make this work better. This is initial work, so you should take it as such. First paper, basically. So what we did is we took workload that we got from Google Transparency Report, and we took following weights onto what we considered was reasonable web presence for different types of jobs. And then we picked out of this 3 worst days we could find. So if you look at peak workloads, we picked those absolute worst days in the whole year. And we figured if we could shave peaks in 3 consecutive worst days, then we should be able to make it whole year without any problem. Right? So that's the results that we're going to see in a second. So first, we looked at centralized UPS. And here, the maximum peak power that we could shave down to was 285 watts, so really not much in a 300-watt server. And the reason for this is obviously the inefficiency of a fully centralized policy. If they do completely localized, you also have a problem because now you have no concept of what else is going on around you. So you start shaving power as soon as it hits whatever the peak was defined. Much better behavior we get when you do rack level and cluster. So at cluster level, we're down to at about 252 watts, which is about 50 watts less than the original, and which gives us much longer durations of power spikes than we could otherwise have. So summarizing all this, we're able to get about 1.5x increase in profit. This is after considering the battery cost, the recharge characteristics, and all of this stuff that I mentioned. If we use energy proportional servers, so imagine this magic world in which power of the server is proportional to utilization, the numbers increase by 2x. Actually, not take it at this value, not the exact effect. The next thing we looked at was energy issues due to the networking, and I'll just touch on this. Current electrical networks are oversubscribed at the level above rack. This, in fact, will cause problems with congestion. So here's an example if I run Rubies alone versus if I run Rubies with a bunch of batch jobs. So I end up with some network congestion. I end up with much bigger response times. This is the log axis. It's a fairly dramatic change in response times. So one of the ways to help this is to actually alleviate some of the congestion by using optical network. So early work in this area was done by Amin Vadad's group at UCSD. They developed Helios optical switch that was able to provide circuit switch capabilities at about 100 millisecond intervals. 100 milliseconds, as you know, is kind of long. So we have since redesigned, and we're now able to do, we advertised 100 microsecond switching time. We can actually do 10 microseconds, except 100 microseconds is our TDMA slot on this optics. So the work that we're doing now looks at how our virtual machines can leverage this mixed optical and electrical network in order to offload the congestion. The obvious target would be to put batch jobs onto the optical network. So this brings me then to global scale. We work with a large NSF project called Translite Starlight that enables us to access wide area optical networks around the globe. So we have collaboration with a number of people in the United States and then in Europe, South America, Australia, and Asia, where we're looking at how to make global data centers and global networks more energy efficient. Part of this is by looking at how we can leverage green energy. So at the beginning of my talk, I mentioned that green energy is not all that easy to do that because it's very variable. One thing that I had not mentioned is that batch jobs, such as MapReduce jobs, have this interesting characteristic that once you launch a job that has a bunch of tasks inside of it, it generally will complete before 30 minutes is out. So given that, and the fact that green energy is variable, if I use prediction to estimate how much green energy I'm likely to get in a 30-minute window, I can perhaps leverage that to run more batch jobs than previously was possible. So that's exactly what we did. Our goal was not to predict green energy for multiple days or even for a single day. It was just to predict it for this window. And that we can do fairly well. We actually got a prediction that has less than 10% error for solar. And this was using a solar array at UCSD. We looked at the data for month of February because it actually rains in February. So we got some variability. We also got data from a wind farm from National Renewable Lab. We have 10 years worth of data from them. These results are actually based on one of the years. Our algorithm gave about 20% error. For wind, that's actually pretty amazing. Typical state-of-the-art algorithms are focused on longer-term prediction, and they give about 50% error. We can do better simply because we're more short-term. And we actually, yes?
How is this power for renewable sources plugged into the power grid for the data center?
So it depends where it is. Our solar array is really close to our container. So we actually have a DC powered rack within the container. So you can take power from solar straight. Wind obviously is not. So in this case, if it were, I could take AC to DC and then back to AC. But in general, people don't do that. In general, you have wind power that's sold to the grid. There are actually some instances of data centers that use wind power locally, and I could point you to a couple of those. Yes?
Is amounts for wind generation black box models, or are they
They use wind direction, wind speed, and past history of power data.
But it's not stupid physics. It's
No,
kind of
no.
straight
We went
physics
for a
analysis.
relatively simple statistical model. The goal was to make it simple enough to use at fairly fine granularity.
So it's not coupled, let's say, with the weather model.
No, but there are very sophisticated models, obviously. We're nowhere close to that. The problem is the sophisticated models have very coarse granularity. Yeah.
And what is the power level of these data centers? Let's say Google, like the DC-DC, AC-DC converters that you're talking about, how big they are? Like 300?
So if you look at large, gigantic Google data center, there's no way you could power it with a wind farm. They don't talk about that. However, if you look at the container level, I can easily power it with one wind turbine. And in fact, one wind turbine would power multiple containers. So it just depends on the scale.
So there are like scales in the order of megawatt or kilowatt?
Yeah, megawatts.
Megawatt. So efficiency plays a big problem in
Yes,
this
it
efficiency
does.
of this
It
station.
does. This is why we're arguing that there is a reason to actually use locally generated power, because you can get rid of some of these inefficiencies. The problem is obviously where do you put this stuff? So in some cases you can. Solar is easier because you can put it on top of buildings and parking lots and so on. Wind power is a little harder to argue. People don't like seeing those turbines. Yeah, that's the thing. But then you can put containers somewhere else. If I have high-speed network, what stops me from putting a container, on the hills where there are lots of wind turbines?
Can I just ask you about your prediction algorithm? Is it really time dependent? So in other words, will your results hold if you look at the longer prediction horizons?
So in this case, it held over a year.
Okay, so essentially for any time you're improving for about 20-something%.
But it's only 30-minute windows, right? So the comparison is not completely fair because the state-of-the-art algorithms focus on completely different time horizons.
Okay, so,
Right.
but if you did a fixed time horizon, would you still improve or?
If we did 24 hours, no. No, this is too simple to do 24 hours. But I don't need 24 hours. That's the whole point. Most of these jobs in data center don't last that long.
So presumably you can repeat your process for every half
Well,
an
that's
hour,
exactly
then
what
you
we do. Actually, we do it more often than that. But you know, at every point in time, the decision is, do I launch more jobs or not, right? And if my prediction is within 20%, you know, I have a fair chance of actually gaining.
But would that mean that, for example, you conclude that you should launch more jobs, but there are more jobs in the queue that the battery will kick in?
So that gets a little more complicated, and I'll actually talk a little bit about the results in a second. So right now what we're assuming is the virtual machine system that I talked to you about earlier that can run services and batch jobs together, and that can control performance for this joint combination. And the question is, how many batch jobs do I want to issue in addition to the service job without necessarily incurring extra cost in terms of power, right? So to do this load balancing both within and across data centers, I need to monitor what is the overall power cost at any individual location. I need to monitor what kind of capabilities I have at any individual location, what's the network availability, and then finally, how much energy do I have? And if all of these things are met, then I'll issue additional jobs, or I'll migrate some of the jobs. So for the network, and this is now wide area network. So imagine the globe, and I have data center containers in many different locations across the globe. As I mentioned earlier, optical links have a fixed cost. Router, however, is not fixed. So we assume state-of-the-art router that actually is fairly flat profile in terms of power. Then we measured one of the newer routers that hasn't quite made it to market yet. We got it from Cisco. And we measured how it would behave if we removed line cards one at a time. So this is the staircase that you see here. There's nothing difficult, actually, about shutting down a line card. The system just wasn't designed from a software perspective to handle it, but you can certainly do it. The red line is just a linear fit to the staircase. Again, you know, this is, I think, fairly reasonably doable. The line that's not reasonable is this purple line, which we call ideally proportional. I don't envision there will be a router that will consume zero power, or near zero power at very low bandwidths. We also evaluated different routing policies. The one that everybody knows is shortest path routing, where we just count the number of hops, and we go with the least number of hops when routing. We developed a green energy aware routing algorithm where we count the number of hops, but we also look at energy cost along those hops and green energy availability. And we'll route through some of the longer paths if the energy cost is low enough and the performance hit is not too high. When we do actual routing of these additional jobs, we looked at two different policies for migrating. One was the jobs use all of the available bandwidth, which means that there is no bandwidth left for anybody else while the jobs are migrating, or that they use necessary bandwidth, and necessary is defined in terms of the time limit. So there is a time limit that's set that basically says everything should migrate by this time. So after all bandwidth policy, there are links that actually don't have bandwidth available, but necessary bandwidth, they do have some bandwidth available. The experimental setup used data centers connected with 100 gigabit per second link. This link has recently been activated between East and West Coast. So a student working at Lawrence Berkeley Lab, where the link actually got activated, we measured power consumption there. We had 5 data centers that were based in different locations in the United States, connected with this 100 gig link. The data centers are basically copies of what we have at UCSD. We allowed for 10% bandwidth in the for background traffic. And we developed then a simulator that estimates all these costs. So we perform measurements for just one of the links, but we actually simulate as if there were multiple. And then for green energy supply, we found that we could get up to 80% of the energy needed per router, depending obviously on what was the source of the energy and what time of the day it was and how much wind blew, for example. And the jobs ran using our vGreen system on the ALM servers in this case, and we guaranteed to meet service time requirements. So to look at the energy benefits, we found that our prediction was able to get 93% green energy efficiency. So this means for every 100 watts of green energy, I was able to effectively use 93 watts to actually get jobs done. This is compared to instantaneous energy use. So if I launch a job and I know that right now power is available, that's basically instantaneous. If power ceases to be available, I'm assuming the job will be terminated. Now you can also assume that you continue running, but at higher cost. Combinations were easier to count. Nobody's going to ask me, how did you get the price? So prediction had 38% more jobs completed versus instantaneous usage. It was about 32% faster, and we found that there are 5 times fewer batch jobs that had to be terminated. This is actually a good study to illustrate to you why this is not done today. So today, data centers are connected using 10 gig links. And if you use a 10 gig link, your performance actually suffers pretty dramatically. So that job completion time, which is on the y-axis, will skyrocket if you start doing migrations. Instead, if you're at 40 gig and above, you can actually do these migrations, and the completion time actually gets better instead of worse. So it's when you move toward 100 gig, you'll see a lot more of this kind of implementation in reality. Looking at average router power, we found that our green energy proportional algorithm actually does obviously better than shortest path. And if you combine it with step proportional router, which is something that's doable today, we can get to the point where routers use only 11% of brown power. So all of the other power comes from green power. To look at performance, our green proportional router is about 7 times better with step proportionality than the state-of-the-art work. It's about 10 times better if we use smooth proportionality, and 30 times better, but this is unrealistic because we use proportionality. So to summarize, I talked to you about a whole bunch of different approaches that we worked on to develop management strategies to enable us to increase energy efficiency in data centers. I wanted to thank both all the funding agencies, both NSF and DARPA and industry. And I also wanted to thank you for your patience and all the good questions. There are a number of other projects we have that I haven't touched on, so if you're interested in talking to me afterwards, I would be happy to do it. Thank you. Yes.
So we talk about this green energy.
Yes.
And just have a, probably can call it a very silly scheme. So let's say I have a lot of battery. And whenever I have green energy, I just recharge the battery. Because whenever it's possible, I just use the battery energy instead of the DC power. So can you comment on this thing and then compare with the algorithm you proposed?
So generally, you can't control exactly how much green energy you have.
Right.
So with solar, the energy tends to come in spurts. In the middle of the day, in sunny San Diego, you'll have a ton of energy, which means that you'll have no trouble charging your batteries, but you'll probably have lots extra that you can use. So it makes a lot of sense to have a scheme that both charges and uses the extra energy.
Since I'm charging and using at the same time. If I charge everything.
And let me actually finish. The other problem is if I just use batteries continually, so instead of using green energy directly, if I first charge and then discharge, I'm going to actually have a problem with lifetime of my battery. So batteries will have limited number of charge and discharge cycles. So I have to be very careful how often I charge and discharge in a 3-year period. So actually, you really do want to have a hybrid solution that's capable of both using batteries for peak power saving and using green energy.
Because in that case, you don't have to care about this prediction. So just say whenever it's available, I just take it. If you have a lot of power,
you in fact do have to care because of the reasons that I told
lifetime.
you. The battery lifetime, and secondly, the fact that you have extra green energy. So you charge the battery, but what do you do with the energy beyond that?
So the energy beyond that.
But perhaps one more point is that as she was saying that energy is much more expensive during a certain time window. And if at that time green energy is not relevant.
I mean, if you have extra green energy that's in the middle of the day, that is more than what you can consume. You still cannot use it.
So green energy generally I can always use. It's never in quantities large enough unless I have a really tiny data center. It won't be in quantities large enough for me to run out of it.
But since
The bigger problem is how long do I have this great amount of green energy? So for example, even in sunny San Diego, you can have a cloud that comes by.
Okay.
Cloud comes above your solar cell, if you happen to be unlucky. The drop in energy that this solar cell produces is really dramatic. So all of a sudden you go from life is good to life is bad, right?
So just want to make sure I understand. So are you saying that using the green energy directly is more efficient or faster than using this green energy to charge the battery?
What I'm arguing for is that you want to do both.
No. What
You
I'm
don't want
saying
to
is,
do one or the
if
other.
you want to charge the battery, you may have extra green energy. But then if you use this green energy directly, you may not have extra. Is that true or?
Depends how you design your system. If you design your system, so then it depends on what you need at a particular time. So if right now I'm running at relatively low utilization, and it's middle of the day, there's no reason for me to use that green energy for peak power shifting necessarily, because there is no peak power that's going above the limit, right? If my battery is already charged, then the obvious thing to do would be to use this green energy to run extra jobs.
There's this incentive because of the nature of the contract with the energy.
Yes.
Right, in other words, if
Exactly.
there was finer granularity,
Yes.
between, for example, depending on various levels you were charging, then what you're suggesting implicitly would make sense.
Yes.
I'm sure Professor Simunic is getting very hungry, and so are you. So we can maybe have one more question. Or we can, right?
Yeah.